Hey guys, welcome to the lecture video on example 10 from your notes packet, which is about basically tetherball. Looks like this. It could also be called a conical pendulum, which is a really fancy word for basically tetherball. But okay, it's more or less if you have something, say, spinning around on the end of a string, and there's going in a circle like this, a nice horizontal circle. That's the kind of scenario we're talking about. The reason I picked this one to look at is because your homework tonight is going to have a conical pendulum on it, and so I thought you might want to see something like this. The other reason is because this is one of those questions that very quickly identifies whether or not people know what direction to put the centrifugal force in. So actually, I'm going to have you pause the video right now and go ahead and draw in the forces. Pause. Pause the video. Don't keep watching. You're supposed to be paused. Okay, great. Now I'll go ahead and write in the forces. So obviously there's a string. So that means that we should have tension. Maybe I'll switch colors here. So, got to have some tension because there's a string there. And it has gravity pulling down on it. All right, and of course gravity's straight down. The one that people frequently will make a mistake on is the direction of the centrifugal force. So if you thought centrifugal force went, say, this way, like opposite the string, that's not actually how centrifugal force generally operates. It goes out from the circle, which is why in this case it's helpful to have the circle drawn on there for you. The centrifugal force would go directly out from the circle. All right. The next thing, now that we've drawn our force diagram, is, let's see, part B wants to know the speed of the pendulum bob in terms of all the other stuff. Now, if you've played tetherball at all, you know that, if you hit the thing just very gently, it's going to kind of lazily wrap around the pole. All right, if you hit it really hard, it swings out really far. So that means that the angle to which this thing swings out has to be related to the speed in some way or another. And that is the relationship that we're going to end up getting out of this particular problem. All right, so if I want to get the speed in here, that means I've got to do something with my centrifugal force. So that would be the x-axis. So let me maybe start by writing an equation for the sum of the horizontal forces. All right, I'm again going to have you pause the video briefly while you try to figure out what are the horizontal forces. Just write that equation. It will involve a trig function. Okay, so pause and figure it out. All right, now that you have resumed the video, having thought about it, you should have, centrifugal force, and then the horizontal component of the tension. All right, now I should note that sometimes in these conical pendulum problems, they do shenanigans with where they put the angle, okay? I put the angle right here, but if they put the angle right there, what trig function you use is going to get switched up. Okay, so given that I put the angle there, and that angle and this angle would be the same, it looks like the cosine component would in fact give me the x component of the tension. All right, so please note a couple of things there. I can't just say centrifugal force minus the tension equals 0, because the tension is at an angle, right? It's only the x component of the tension that opposes the centrifugal force and keeps it moving in the circular path. All right, now, if they gave you the angle from here, from the vertical, then it would be like all of those inclined plane problems that we've been doing where x and y are switched from your normal expectations. If they give you the angle from the vertical now, all of a sudden, the sine component corresponds to the x direction. All right, so that tends to get people a little bit mixed up. but just as long as you recognize where they gave you the angle from, and therefore the fact that the opposite side now corresponds to x, you're going to be okay. All right, I'm pretty sure they did do that in the homework, so just be aware they switched it up. Sine is going to be the x components because of them giving the angle from vertical and not from the horizontal. All right, now I can plug in my equation for centrifugal force, and I can say, equals t cosine theta. And, all right, now I am doing this like a symbolic problem, okay? So I didn't give you any numbers here. You'll note that it says, find the speed in terms of m, l, theta, and g. So if I went and solved for v, I would have the tension in there. The tension is not a given in the problem, nor should it be, because the fact of the matter is that if this thing is moving faster, the tension is going to be greater. The tension also is a function of how far out the thing swings. So the tension is different depending on how fast that pendulum is moving, or tetherball. So that means that in order to solve this for v, I actually need my y equation as well, because I have two unknowns. I don't know v, and I don't know t. All right, so let's switch to my y equation. All right, in the y direction, all right, again, you should pause the video and write the equation for the y direction and see if you got it right. All right, here I go. mg minus the vertical component of the tension, which in this case would be t sine theta, because I gave the angle from the horizontal. Okay, and from this equation, I can actually go ahead and solve for the tension. All right, so let's see. That actually ends up being part C, so we'll have to go back to part B. I don't know why I gave the question in that order in retrospect. The tension then would be, all right, if I move that over by adding it to both sides, it's mg over sine theta. All right, there's my tension. All right, now that I know that's the tension, I can go ahead and substitute it back up in here. All right, so now this side of the equation will say mg over sine theta times cosine theta. All right, if you look at that, you're thinking, aha, can't I do something with sine over cosine as tangent? You absolutely can. We could turn this into mg over tan theta. Or if you prefer, you could also say it's mg cotan theta. If you're not okay with secant and cosecant and cotangent, don't worry about that. You may not have seen those yet in your math class, I don't know. Mg over tan theta is just fine by me. All right. Right, so then the goal was to solve for the speed. All right, so again, you should pause the video, see if you can solve for speed, but there is one quirk that you need to compensate for. I will warn you before you try and pause, and that is that r is not the length of the rope. R is not the length of the rope. All right, so pause, figure out what r is, and then go ahead and solve that equation for v. All right, now that you've resumed the video, here we go. So r is this distance right here, right? That is the radius of the circle, which I guess you could say is also a function of the speed, right? How fast it's going. Fortunately, though, it's also in terms of L and some trig function. All right, so I'll use this triangle up here, since that's the radius, and that's also the radius. Or I guess I could be using this down here. Well, whatever. Either way, the hypotenuse is L, and the angle here is theta. and the radius is the adjacent side. So that means that the radius would be L cosine theta. All right, if you're not comfortable with that, then you should draw out that triangle and go through the trigonometry and solve for it, see if you can make it work. All right, so if R is L cosine theta, let me take these two halves and rewrite them over here. And that equals mg over tan theta. All right, the mass will cancel out. All right, so in theory, you could play tetherball with a bowling ball, and you get the same relationship between the angle and the speed. It'd be less comfortable playing with a bowling ball for you, but in terms of the speed and the angle, it would be an identical relationship. So the mass is unimportant. All right, so then v squared will equal gl cosine theta over tangent theta. All right, so therefore the speed is the square root of that. Okay. All right, now let's see. Part D, what tension is required in order for theta to be 0? All right, this right here is actually just, it's a conceptual question, all right? And it's kind of like earlier when we were talking about, all right, why is it that when you hang up a rope, it always sags a little bit in the middle? No matter what you do, okay? If you take a rope, tie it between two trees or whatever, it's always going to sag a little bit in the middle, no matter how tightly you pull it, because there will always be a component of gravity pulling down, because the rope has weight. And therefore, if the tensions are completely horizontal, they can't hold up the middle of the rope. So there always has to be a little bit of sag to the middle of the rope, because it needs to have an angle, just a slight angle maybe, in the upwards direction so that the tension has a vertical component. The same thing will be true here. If this swings out actually completely horizontal, it won't be stable there, right? Maybe for an instant, if you hit the tetherball up really hard or something, right? It might go horizontal or even go past horizontal, but it will not rotate stably in a horizontal circle, no matter how fast you make it go. Because if the tension is completely horizontal and the centrifugal force is completely horizontal and gravity is down, there's no vertical force opposing gravity, and so it will have to fall downwards a little bit. All right, now you could also show that it's an impossible result by just plugging in 0 degrees. And if you put in tangent of 0, you get, I believe, 0. Yeah, since it's opposite over adjacent at 0 degrees, it would be 0. And you can't divide by 0. Right? Or at least in calculus, you will discover that if you have 0 in the denominator, you get infinity a lot of the time. So that is what this would say, is in order for it to be completely horizontal, it needs to be moving infinitely fast, which will obviously snap the rope, and therefore not be okay. All right, I hope that helps you with the conical pendulum problem in tonight's homework. So there you are.